Hello, today we are going to give a small presentation on computational algorithm to optimize teaching scheduling, which is our final project for CHE 531 Numerical Methods in Chemical Engineering course. The group members are Milos Markovic and myself Kartikeya Sharma. Let's begin. Motivation for this project. Presently, the number of courses at the university level have quadrupled, and because of this, allocating courses to teachers according to their preference has become a very difficult task. The fairness in the allocation process is presently arbitrary and sometimes unsatisfactory. Simplex method taught in CHE 531 can be used to optimize the objective function to ensure fairness in this process. So let's discuss how the simplex method can be used. Simplex method. Simplex method consists of 5 simple steps. First is objective function. We have to define an objective function for our problem. Then second is constraint and variables which program will take into consideration while optimizing our objective function. Third is lower and upper bounds on the variables of the program. Fourth is making A and B matrix which are inequality matrix, and A equality and B equality matrix which are equality constraint matrices. And fifth is solving using linprog in Matlab. Let's discuss this further in detail. Objective function. Objective function in this project is defined as summation over multiplication of Wi and preference ij, where Wi is the weightage of the preference 1, 2, or 3, and preference ij is preference j of teacher I. For example, this is the first weightage, that is first which is 1, multiplied with the first preference of first teacher, then addition of second weightage, that is 2, and multiplied with second preference of first teacher, then addition of third weightage multiplied with preference of first teacher and third preference. Similarly, this is for second teacher. Now let's discuss the constraints and bounds which are applied on this which are applied in this program. Let's discuss constraints and bounds. There are 3 types of constraint. First constraint is every class must be allocated only and only once. Second is all class must be allocated. Third is each teacher should get only one preference. And bounds as each preference should be either between 0 or 1, indicating which preference a particular teacher has got. Either the first preference, second preference, or third preference. Let's discuss how the A equivalent and B equivalent matrix for 3 teachers and 3 preferences with 2 subjects mm, can be formed. In this figure number 1, we can see that the columns are for teachers, and for each teacher there are 3 columns for preference 1, preference 2, and preference 3. Similarly, for teacher 2 there is preference 1, preference 2, and preference 3. Each row is one course. There are 6 courses in total, so there are 6 rows. So course 1, course 2, course 3, course 4, course 5, course 6. If you can see, this whole row represents the course 1 and different preferences. This one represents over here that teacher 1, preference 1, there's the course 1 was there mentioned once. Then the course 1 was not mentioned in any of the preferences of other 2 preferences for teacher 1. Then for teacher 2, the course 1 was not mentioned in the first 2 preferences but for the third preference, and teacher 3 did not mention course 1 in any of their preferences. And this whole equation, we can say, or line, should be equal to 1. That means either teacher 2 will get the course 1 or teacher 1 will get course 1. And if you can see, the teacher 1 should get the course 1 because this is his first preference, and teacher second per third preference was course 1. Similarly, this is done for all the courses, and the last 3 rows are for third preference, that is each teacher should get only one preference. Over here, if you can see, there's in this row it says 1 1 1 and all the zeros. That means either 3 of these rows can be 1, because this whole row should be equal to 1. So either preference 1 should be equal to 1, preference 2 equal to 1, or preference 3 equal to 1. That means either one of the preferences can be equal to 1, which means that only one preference can be given to any one teacher. Similarly, second row is for second teacher, which says that this is 0 because this is for second teacher, and all the preferences for teacher 2 is equal to 1, which means that only one of the preferences of teacher 2 can be allotted, and similarly for teacher 3. Let's now discuss the Matlab simulation itself, which will be discussed by Milos.
Let's look at the Matlab simulation. In the left-hand figure, the user will be met with an initial input window when they first run the algorithm. The initial inputs are the number of semesters, either 1 or 2, and the number of teachers, and the preferences per teacher. All of these inputs are required to move on to the next step. This window now takes us to the figure on the right-hand side, where these initial inputs are incorporated. The tables represent the inputs per that semester. Since the example had inputted 2 semesters, 2 tables are shown. If only 1 semester was desired, then only the top table would be available. The top one represents the first semester and the bottom represents the second semester. There will be X amount of windows that will pop up after the initial window, where X is the amount of teachers. In this example, the user would be met with 11 individual pop-ups. And finally, the preference per teacher is reflected in both tables. The user can input as many classes per preference as they wish, but only up to 3 preferences as shown in this example.
Let's discuss the results. In the results section, we have figure number 4 and figure number 5. Figure number 4 shows the input data values for spring and fall semesters with marked optimum results, and figure 5 shows the output from Matlab using Simplex method. If we see each for input, we have 11 teachers and each teacher has been given 3 preferences, but the number of courses in each for each teacher has not been fixed. For example, for Dr. Shafiq Mareen, he wants to teach 3 courses in fall semester, but Dr. Minesh Singh wants to take only 1 course in fall semester. So this gives us flexibility in allocating the courses. The highlighted courses over here shows the optimum results, and we can match these results with the original results from the MATLAB. If we see for Dr. Shafiq Mareen for fall semesters, the allocated courses is in preference 1, not in preference 2, not in preference 3, but in preference 1, which are 201, 499, and 520. And over here for fall semester in Dr. Shafiq Mareen's section, we can see the courses allocated are 201, 499, and 520. Let's take another example from spring semester. For spring semester for Dr. Vivek Sharma, the course allocated is in preference 1, which is 321, 341, and 592. And if you see Dr. Vivek Sharma's results for spring is 321, 341, and 592. So this is for matching the results, and we can see that some of the professors uh, did get preference 2 and even preference 3, but that is done to optimize the overall fairness in the objective function or in the allocation of courses to the teachers. Now let's go to the next slide. In this slide, we have figure 6a and 6b, which are compared against figure 4. This is how we get results from the MATLAB, and we can understand that these matrices using our input data. So over here, all the columns are for teachers. There are 11 columns, and those are for 11 teachers, and each row represents preference. So this is preference 1, preference 2, preference 3, and 0 and 0 over here means that this particular teacher got his first preference, while this particular teacher got his second preference. So first teacher was Dr. Shafiq Mareen, and he got his first preference, which is mentioned over here, which is 1 in the first row and first column, which is the first and exactly the optimum course highlighted over here is the first course, first preference. Similarly, for spring semester, if we see that for Dr. Shafiq Mareen, that is the first teacher, and the preference allocated is first preference, not the second preference and not the third preference. And exactly, if you can see over here, the optimum the course that was allocated was preference 1. And if you want to see some other example, we can see that for the 11th teacher in spring semester, the course the preference allocated was preference 1, not preference 2, not preference 3. And for the 11th teacher over here, the preference allocated was preference 1 indeed. Now we'll move to the feature and failsafes that is inbuilt in the programming, and this will be discussed by Milos.
Now we'll go through a few features and failsafes that the algorithm has built in it to ensure that it runs as smoothly as possible. The algorithm has 4 failsafes built into it before any problem solving occurs. The first failsafe is making sure all classes exist. If the algorithm encounters any inputted classes that isn't previously registered in the code as a viable class, then the code will pause, and ask the user to re-input the selection of the courses of that teacher for which an error was found. In this example, class 200 was invalid, so the code would stop running and re-ask for the input once it notices the error. The second failsafe is making sure each class that needs to be taught is mentioned at least once. Once all the desired inputs have been completed, the algorithm will then make sure that each class was mentioned. If not, the algorithm will then notify the user that there is a class missing, which class that is, and will stop any further execution. In this example, class 105 is missing from the pool. The third failsafe is making sure there are no duplicate preferences per teacher input. If a teacher ends up creating a preference whose contents are the same as another, the algorithm will notice this, pause, let the user know there is an error, and request that the user re-input the preferences for that teacher whose input caused the error. In this example, for teacher 1, preferences 1 and 3 are the same. The fourth and final failsafe is making sure there are no duplicate classes per the same preference. When the user has inputted all the preferences for a teacher, the algorithm will then go through each individual preference for that teacher and identify if there are any duplicates. If a duplicate was found, the algorithm will pause, let the user know there's an error, and request that the user re-input the preferences for that teacher whose input caused the error. In this example, for teacher 1, in preference 2, they provided class 102 twice within the same preference. In conclusion, the simplex method is an easy and efficient way for linear optimization problem. Our algorithm has the following features in summary. It can solve for 2 semesters. It can accommodate many number of teachers. We've shown it accommodate 11. It can solve for more than 30 courses. It can account for different number of courses per teacher. It can also account for different number of courses per preference per teacher. It solves for all the courses and checks for duplicity in preferences. And it saves time and work put into solving this problem manually. Finally, on behalf of me and Kartiki, thank you.